hall room. Next week we're moving to our permanent place in Win 5409. We still have oversubscription to the course. I'm going to do my best to reduce it. But I'd like to try to accommodate anybody who still wants to stick with the course. If you, or more likely your friend, are registered for the course and know that they're not going to take it, know they're going to drop it, please ask them to do it sooner rather than later, so that people on the waiting list can be cleared in. I assume that if you're here, you're probably not sure that you're going to drop it. If you're on the waiting list, please hang in there. The official drop period is, I think the deadline is this coming Monday. I assume that by then, judging by every year, by then some people drop the course and then there's more room. If you have any particularly unusual circumstances that you must take this course and you're still on the waiting list, do write to me. I did hear from some of you, and I took it under advisement, and we'll just have to see what the situation is. There's limited capacity in that lecture room. Okay, we have an assignment out. It's due on Tuesday before class starts. There will be another assignment out on Tuesday at the end of class. Will be due a week later. What we'll talk about today is information theory. It's not covered in the book, although it's covered in many other books. I'm going to cover the very basics. What I've found already years ago is that somehow there's a gaping hole in the curriculum of computer science, not just here but just about everywhere. Somehow there's this little niche information theory thing that is not covered anywhere else. And it is certainly needed and useful for machine learning, but it's actually needed and useful in many other areas. So I just decided to incorporate this part of the machine learning course. What I'll be talking about is basically 4 concepts. We're going to cover all 4 in sequence. We'll get as far as we can today, and we'll continue next time on Tuesday, and we probably will not need the entire Tuesday. These are our 4 topics. At the very end, the connection to machine learning will be made. So let's talk about information first. Just like when we talk about machine learning, there's a meaning of learning that's used in everyday life, which is not the meaning that we're using in machine learning. We make a much more quantitative, objective definition of learning than what you typically use in everyday life. Same thing goes with information. Information is a very loaded word. It means lots of things to different people. We're going to define it very narrowly and very concretely. And the definition would have to do with knowing which of any number of possible events happened. So we know in advance a set of possible events. We know that exactly one of them is going to happen, and when we know that one of them happened, we received information, some amount of information. So it could be the classic case of flipping a coin. Let's assume that it can only result in head or tail. In this case, there are only two possible outcomes, and when we know which one it is that happened in this particular flip, we got some information. Okay? Or it could be a die, a six-sided die. There are six possible outcomes. We don't know which one is more likely, we don't know which one is going to happen, but when we do find out which one happened, we got some information. Before we got the information, we had some uncertainty. In the case of the coin, the uncertainty was, is it going to land on head or tail? After we got the information, our uncertainty with regard to this particular experiment goes down to zero. No uncertainty. So we can equate information with reduction in uncertainty. Okay? So information is going to be defined as reduction in uncertainty. This is useful because sometimes we will not reduce uncertainty to zero. If you toss a die and it has six possible faces, and somebody else does it for you and they tell you that the result is odd, is an odd number, you know it's either 1, 3, or 5. You got some information. Your uncertainty was reduced. Very roughly speaking, it was reduced from 6 possible outcomes to 3 possible outcomes. Not necessarily equally likely, but 3 possible outcomes. So you had a reduction in uncertainty, that means you got some information. You could argue you got less information than you would get if you found out exactly which face it landed on. When there's nothing left uncertain, your uncertainty is 0, and you cannot get any more information from that situation. Okay? So this is the motivation or the intuition. Now let me give you an exact definition of information. You have a set of possible events of, say, complementing mutually exclusive events, E1, E2, E3, up to, say, En. We don't have to stop at En, it could be an infinite set. That would work fine too. They each have some probability with associated probability of occurrence. Of occurrence. P of E1, P of E2, and so forth. Now you are told, please. Well, based on the way I define it here, they're complementary and they're mutually exclusive. By complementary I mean that they form the entire set, so they form a partition. In this case they will sum to 1. It turns out that for our definition it's not strictly necessary. They could be overlapping. But for our simple story here, let's assume that they are, you just take the event space and divide it into mutually exclusive compartments. Now here's the definition of information. If you now found out that event I happened, now you're told, that event E sub I happened. Then Then you received information. And the information you received we'll call it I, is defined as log of 1 over the probability of the event that you observed. Where did this strange formula come from? Y log, Y 1 over P. Let's first see if it makes sense. Suppose the entire space of events had exactly one event. Or it had more than one event, but one of them had probability of 1, and all the others had probability of 0. So suppose the event is the sun will rise tomorrow. And all other events, such as the sun will not rise tomorrow, 3 suns will rise tomorrow, whatever, have probability 0. But you know with certainty, don't ask me why, suppose you know with certainty that the sun will rise tomorrow. The probability of that is 1. You go to sleep, you wake up in the morning, the sun did rise. You want to know how much information you got. P of the event is 1. 1 over 1 is 1. Log of 1 is 0. You got 0 information. That's not surprising, that's intuitive, that's what you want to get, right? That if there's an event that's going to happen for sure, then knowing that it happened doesn't give you any information. You could argue that in reality it's never the case that you know something for sure, and I would agree. But in the extreme case, that you're anticipating something that has probability 1 of occurring, when it occurred you got no information. Now take the other extreme. Suppose you woke up in the morning and the sun did not rise. How much information did you get? Right. Infinite information. Okay, so what does that mean? Let me equate information with surprise. Okay? So there are 2 useful ways of thinking about it. One is information, the other is surprise. So in the first case, when the sun did rise, you were not surprised at all. Your surprise is 0. In the second case, when the sun did not rise, your surprise is infinite. You're infinitely surprised. As well you should be. If you believe that something cannot happen, and it happened, you should be infinitely surprised. If you believe that something is very unlikely to happen, and it happened, you should be somewhat surprised. Right? The more unlikely it is, the more surprised you should be. You buy a ticket to the lottery. It has 10 million tickets. You don't expect to win, but there's some small chance you will. If you find out that you did win, how surprised are you? Well, 1 over probability of win is 1 over 10 million, right? So 1 over 10 million is 10 million. Log of 10 million is a fairly large number. So you're very surprised. Question?
So, in the case that the sun doesn't rise, E of E, is still 1 because you're still sure that it rises. So how does that give you?
No, the E that you put in here is the E that actually happened. So in the case of the sun, the set that you have is E1 is sun will rise. E2 is sun will not rise. P1 is 1, P2 is 0. Okay? So, if the sun did rise, this is E1, this becomes 0. If the sun did not rise, this is E2, and this becomes infinite. I didn't tell you what the base of the log is. Right? Different logs have different bases, you get different numbers. What do you suggest? I'm sorry? It doesn't matter. Changing the base of the log will change the amount by a linear factor. Right? So it's the same as measuring information in miles or kilometers or grams versus ounces or whatever. It will determine the unit of measurement. You can use any base you want. It is convenient for us to use base 2. So we will use base 2, but we don't have to. When you use base 2, the units of measuring information are bits. So take the case of a fair coin, a coin that is equally likely to fall on head or on tail. You flip the coin, it landed on head. How much information did you get? One bit. Okay, why is that? It's 1/2 here. 1/1/2 is 2. Log base 2 of 2 is 1. 1 bit. What if it landed on tail? Same thing, you also get 1 bit. So for a fair coin, even before you know the outcome, you know you're going to get 1 bit. That is not true for an unfair coin. If you have a heavily weighted coin that has the probability of 0.9 of falling on head and 0.1 of falling on tail, when do you get more information? When it falls on head or when it falls on tail? Loud, please. Tail. When the rare event happens, you get more information. But of course, that will happen more rarely. So if you flip the coin many, many times, most of the time you get very little information. Every now and then you get a lot of information. And you may want to ask yourself, on average, do you get more information from an unfair coin or from a fair coin? That's a good question to ask. Please. You know, there's some helicopter making noises out there, so if you can speak louder, I would appreciate it. Thank you so much. This is an excellent point. So the point is that the probability we're discussing here are in your mind. One could argue that all probabilities are in your mind. But it's a very important point. It means that the notion of information is a subjective notion. If two different people approach a situation and they have different assessments of the probability of events, their level of uncertainty in their mind is different before they start, and the amount of information they get is different. If you are an astronomer and you know it's going to be the sun is not going to rise tomorrow for some strange reason, then you adjusted your probabilities and you're less surprised when it happens. If you're the magician and you know that the coin is heavily biased or weighted, then you're not that surprised or the other way around. But the idea is that if you have a different assessment of the probabilities, the numbers you get out are different. So information is not just a measure of something in the environment, it's a measure of interaction between what happens in the environment and what was in your head before, what your expectations were. There are some limits. Information cannot be negative. Why is that? Right, for information to be negative, this would have to be negative, which means this would have to be greater than 1, which means this would have to be, this would have to be lower than 1, which means this would have to be greater than 1. Probabilities are between 0 and 1, and therefore information is never negative. Okay, suppose you have a fair die with 6 faces. each face is equally likely. You roll it and it landed on face number 3. How much information did you get? Sorry?
1 over 6.
Didn't hear that.
1 over 6.
1? Log base 2 of 6. So the event space is the 6 spaces. 1, 2, 3, 4, 5, and 6. These are just the names of the faces. They could be named anything. And the probability distribution over them is 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. Because it's a fair die, no matter which one it landed on, let's say this one, 1 over P of the event, log of that. P of the event is 1/6, 1 over 1/6 is 6, log base 2 of 6 is log base 2 of 6, which is about 2 point something bits. How many? 2.585. 5 bits. Compare that to flipping a coin, where you get exactly 1 bit, a fair coin. So if you observe 2 streams, one streams of coin flips and one stream of die flips, you can say that you get more information out of the die flips or die tossing than out of the coin flips. Or alternatively, you can say that there's more uncertainty in the experiment of tossing die than of flipping a coin. And it's a very quantitative statement. You can say by how much more. In fact, tossing 1,000 dies is roughly equivalent to flipping 2,585 coins. Okay, you can make it very concrete, very quantitative. Assuming both the coin and the die are fair. Okay, one important property of information as defined here is that it's additive. What do I mean by that? I mean that you can, in fact, the statement I just made earlier about 1,000 die tosses versus 2,585 coin tosses was assuming additivity of information. It means that if you have 2 experiments in a row, you can view them as one single experiment with a joint space of outcome and calculate the amount of information there, or you can break it down into 2 components, calculate the information in each one alone and add them together, and the result should be the same. That's what additivity means. So alternatively, you can take a complicated experiment and break it down into components and calculate the information in each component. Now hopefully there's something going on in your mind that says, well, there may be some correlation between them, there may be some dependence. Yes, that's true. And if there is dependence, you have to take it into account, and I'll show you how. But in principle, you can break things into components, calculate information in each component, and add them together. So let's do it with a simple case of tossing a coin k times. First, let's take it and do it as k separate experiments. We know that it's a fair coin, and we already calculated that each time you toss a coin, you get 1 bit of information. So from k coins, you get, from k experiments in a row, you get k bits. Okay? But now let's look at it a slightly different way. Let's think that it's a single experiment where you tossed k coins in a row and you recorded the result. So an outcome of such an experiment would be a sequence of k values like head, tail, 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 head, up to position k. Okay? There are many possible outcomes now, not just 2. How many possible outcomes are there? 2 to the k. What is the probability of each one of these outcomes? Each one of these outcomes, because this is a fair coin, has a probability of 1 over 2 to the k. Right? So regardless of which one happened, when you're done with the experiment with k tosses, you got how much information? 1 over this log base 2. 1 over 2 to the k is 2 to the k. Log base 2 of 2 to the k is k. So there are k bits in a serial experiment of independent tosses of a coin, a fair coin. And you can calculate it either as a single experiment or break it down. Why is this important? Because now we can calculate the amount of information in very large systems. For example, suppose you're generating words, you're generating sentences at random. You have a large dictionary of, say, 100,000 words, and you take a word at random, a uniform probability from that dictionary. What is the amount of information that you get when you see the word that was chosen? The amount of information you get from choosing a specific word is log base 2 of 1 over the probability of each word, which is 1 over 100,000, which comes to log base 2 of 100,000, which comes to 16.61 bits. And now suppose you generate many words in a row until you have a document of 1,000 words. Because information is additive, and because you generate these words independent of each other, we can immediately say that the document of 1,000 words is simply 1,000 times this. So it's 16,661 bits. Again, assuming you have a vocabulary of 100,000 words, assuming that every word is equally likely. You can imagine being a little smarter than that when you generate your document. I mean, you can generate it such that more common words like the are more likely to come out. You can generate it in such a way that the next word, the probability of the next word would depend on the word that you generated before. I mean, you can make it look more and more like English. But if you just leave the very simple thing of just generating words at random, this is the amount of information in a document. Now compare that to the amount of information on a small screen. Visual information. Suppose you have a quarter VGA screen, and you guys probably don't even know what a quarter VGA is. You probably have these high resolution screens, but I guess a cell phone these days probably has 480 by 640. Is that right? 480 by 640 pixels. Suppose you generate a random image by taking each one of these pixels and choosing a grayscale level for it. It's a black and white screen, but it has grayscale level. It has 16 levels, represented by 4 bits. 16 level grayscale. What's the amount of information that you get by generating a random small screen like that? The amount of information per pixel, since the pixel has 16 possible values and each one is equally likely, you should know by now, is log base 2 of 16. That would be 4, right? You can see that by the fact that you need 4 bits to represent that grayscale value. It all looks the same as long as all of them are equally likely a priori. Once they're not, things change. But it's 4 bits here. And here, how many such pixels are there? (307,200) times 4 bits gives you 1.228 bits. More than 1 million bits. Now compare the amount of information in a document of 1,000 words to the amount of information in a small grayscale screen. A lot more on the screen, right? Or as the saying goes, a picture is worth 1,000 words. In fact, it's worth a lot more than 1,000 words. Now granted, both of these measures are very conservative. If you had a more accurate model of text, the amount of information would be much smaller. We will talk about this the rest of today and next lecture on Tuesday. But the same thing is true for the image. Not all images are equally likely. And we don't generate images at random, and suddenly we don't find images at random. If you point your camera at some nature scene, you don't get a random image. You get an image that comes from some distribution that's far from random. So I'm sort of fast-forwarding to the end and telling you that when that's the situation, the amount of information you get is actually much smaller. This is in fact an upper bound. But it still gives you a rough idea of the relationship between the amount of information in image and in text. Image has a lot more information. Okay, any questions about information? All right. Let's talk about entropy. If you understand information, entropy flows naturally. Imagine that you have a repeatable experiment, like a repeated coin toss, or repeated generation of words or of images. Alternatively, you can think about it as a source of outcomes. Some box that when you push a button, an experiment happens and you get the result. And suppose you stand there and push the button all the time, you keep getting outcomes. So if it's flipping a coin, you keep getting head, tail, head, whatever it is. So now don't think about a single experiment, but think about a stream of these experiments. If the coin is not fair, then sometimes you get an event that's more likely and sometimes you get an event that's less likely. When you get an event that's less likely, you're more surprised. When you get an event that's more likely, you're less surprised. Now if you think of yourself as being subjected to this long stream, you can ask about what is the average surprise in that stream. So all entropy is, it's the average information in a process, or average surprise. If at the end of observing your uncertainty was reduced to 0, you can also define entropy as the average uncertainty in a situation, or rather the uncertainty. So entropy should be written as H of a probability distribution P. It's a function of the probability distribution because it's determined completely by the probabilities of the different outcomes. So think about a source, think about a black box with a button that you push and you keep getting events, but the events are interpreted, as was pointed out here, interpreted by you relative to your belief about how likely they are. What is it's defined as the expected information, expected under the probability distribution P. How is expectation defined? It's summation over all possible events. The probability of each event is Pi times the information content of that event. So when you're about to push the button, you say there is some probability that this event will happen, in which case I will be this much surprised, and there's some probability that that event will happen, in this case I'll be that much surprised, and you sum over all possible events. And if I expand the definition of information, I get pi times log of 1 over pi. Pi is the same as P of E of I. And if you want to write it a little differently, you could write it like this: P of I times log of P of I, and you have a negative sign here. Same thing. And some of you may have seen this form of entropy. Now, the term entropy has been used in many, many areas. It has a very concrete meaning in physics. There's been a lot written about the relationship between entropy as a concept in physics and entropy as a concept in information theory. There's clearly a relationship. The formulas are very, very similar. The intuition is sometimes quite different. So you would find some people who would tell you that they are one and the same, that it's the same thing. And some people would tell you that they're not. There's a funny anecdote. Information theory is a relatively new field. It was invented in the late 40s by Claude Shannon. He was a scientist working at AT&T Labs, or I think it was called Bell Labs at the time. When he came up with this notion of entropy, often he was asked why he chose to call it entropy, because it generated so much controversy. Is it the same as the entropy in physics or not? And entropy in physics itself is a difficult concept to grasp sometimes. And at some point he wrote, I don't know if he really meant it or not, that the reason he chose entropy, the term entropy, is because nobody understands entropy, so nobody could object to it. When entropy is used, information theory is often called Shannon entropy, as opposed to the kind of entropy that has been used for at least 100 years before in statistical mechanics and other branches of physics. We can understand entropy in many different ways. We already defined it as the average amount of information provided per symbol. Per event. I call it symbols in my slides, but here I stick to the notion of events. So if you push the button and you keep getting event outcomes, the average amount of information per event is the entropy. Alternatively, you can think about it as the average amount of surprise when observing an event, because the actual amount of surprise varies, goes up and down depending on how rare the event is. You can define entropy as the amount of uncertainty before observing an event. And here's another definition which is maybe less obvious or less intuitive. Turns out that entropy is the average number of bits. Or let me start a different way. If you wanted to create a code to communicate the outcome of the experiments, and you wanted your code to be as efficient as possible, on average, suppose you have to communicate with someone what the coin flip result was, or what the die toss result was, but you anticipate that you have to communicate the results of many experiments. So you want to devise efficient code so that on average you send as few bits as possible. On average. It turns out that the entropy of the process is a lower bound on the number of bits you need. Namely, there is no code that can communicate the result of the experiments with less than the number of bits on average. With less than the number of bits as indicated by the entropy. So if the entropy is 3.75, there is no code that on average would use less than 3.75 bits. That was one of the first results by Claude Shannon. Another similar related result is that there actually are codes that will communicate it with exactly 3.75 bits. So not only is it an upper bound, but it's an achievable, also a lower bound. It's an achievable lower bound. You can create a code that would use exactly this many bits on average. Although to actually achieve exactly that bound, sometimes the code needs to be incredibly complicated. In reality, you often compromise and you find codes that are much simpler, but instead of using an average of 3.75 bits, they might use 3.8 bits. This relationship between coding efficiency and information is very, very deep. It's worth thinking about. How many of you have ever compressed text files? I suspect that even those who don't raise their hands probably did it and didn't realize they were doing it. If you work in Unix, then you're familiar with the compress function. If you work in Windows or something, zip probably does that for you. Do you remember or do you know roughly what's the rate of compression is for text files? You take I'm sorry? 3 or 4. Yeah. If you take a regular plain old English text file and you run compress on it, the resulting file is about 1/3 the size of the original. What does that mean in terms of the amount of information that was in the file in the first place? This is non-lossy compression, meaning that it is possible to reconstruct the original file without loss of accuracy. So all the information that was in the original file is somehow in the compressed file. How is it possible that all the information can be put into a smaller place? The only reason it's possible is because the information is redundant. Right? The simplest form is redundancy. If you have one letter that repeats 12 times, you can just write 12x. If it's T repeats 12 times, you can write 12xt, and that takes only 1, 2, 3, 4 characters, and you know that that means a run of 12. Okay? You can invent your own ways of writing things in shorthand, but in principle, the only way you can actually compress text is if text does not contain as much information as is taken by the bits of regular representation. So when you compress text by a factor of 3, that means that if you had a document of 1,000 words, and that took an average of, say, 6,000 characters, 6,000 bytes, that goes down to 2,000. You could say that the inherent amount of information in a document is no more than 2,000 bytes. It might be less, because maybe somebody else has an even better compression program that will compress it even more. In fact, it's hard to tell how much more, what is the limit of compression. How do you know that somebody might not come up with something even smarter and would compress it even more? But you know that if they are able to compress it by a factor of 3, then at least it's the case that the original text contains no more than 2,000 characters worth of information. This notion of compressibility, or equivalently of efficient code, right? An efficient code you can think of as a form of compression. They're kind of the same thing. You get efficient by removing redundancy. It's not always good to be efficient, because if you remove all redundancy, what happens if there is an error on transmission? Removing all redundancy means that any string of bits that you send looks plausible. Redundancy is sort of a sanity check. You guys familiar with how checksum works? You submit 8 bits of a character, and you submit a 9th bit that counts whether the number of on bits is even or odd. So that way, if one of these 9 bits is corrupt and change its value, things don't add up at the other end, and at least the other side, the receiver, knows that something is wrong. They might not know what to correct, but they know something's wrong. They can ask for you to send it again. This is an example of deliberately introduced redundancy. Information content, entropy, compressibility, coding efficiency, they're all one and the same. Questions? Okay. What are the properties of entropy? Can entropy be negative? No. We know that information cannot be negative, and entropy is the average information. An average of a quantity that's not negative cannot be negative. Okay, so entropy of any distribution is always greater or equal 0. When will entropy be 0? Under what conditions will the entropy be exactly 0? Please.
When you know the outcome.
When you know the outcome. When there's one event that has probability 1 and all other events have probability 0. If you plug it into this equation, for that event that has probability 1, this is 1. This is 1 over 1. Log of 1 is 0. And for the events that have probability 0, this becomes infinite and this becomes 0. But if you took calculus and if you think about it as a limiting process where this goes towards 0, you know that this goes towards 0 faster than the log. So if you want to define probability 0 as a limit of very small probabilities, the entropy would go to 0. So the only case when entropy is 0 is when there's just effectively just one outcome, known in advance. As long as there's any uncertainty, the entropy would be greater than 0. Okay, what about an upper bound on the entropy? Can you put an upper bound? What's the most it could be? Let's say for a fixed situation with k possible outcomes. I'm writing here, instead of big P with a bar over it, I'm writing here explicitly the distribution P1, P2, P3, all the way through Pk. It's the same thing. We're assuming here that these sum to 1. We know that this is always greater or equal 0. Is there an upper bound? Is there a value it cannot be greater than?
If the highest possible event occurs always.
The highest?
If the most informative event occurs all the times.
The most informative event occurs all the time. What I think you're saying is that you would be most surprised if the most surprising event happens all the time, and then you would get the most information. That is true, but this is not what entropy is about. Entropy talks about the average surprise, and the average is over the likelihood of each event. So you must weigh your surprise by how likely is this surprise to occur. It's a long-term average, which is calculated by summing over probability or expectation. There is an upper limit. Please. Log of k. It cannot be greater than log of k. And when does it achieve log of k? In the case where all events are equally likely. So we already discussed these cases of a fair coin or a fair die. And it's clear that it's log of k then, because each event has probability of 1 over k and 1 over 1 over k, etc. Please? That's exactly what it means. Absolutely. So one conclusion you can draw is that a fair coin gives you more information. By tossing a fair coin you get more information than by tossing any unfair coin. So this event happens, this is equal if and only if Pi equals 1 over k for every I. It happens only in the case when they're equal. As soon as they're not equal, this inequality kicks in and the actual entropy is lower than log k. Let's take the special case of k equal 2. So flipping a coin. We can calculate when k equals 2, we have just P1 and P2, and they sum to 1. So we can actually represent it with one parameter. Let's say P1. Or we can call it P head and P tail. P tail is 1. So we can represent it by the parameter P head with the implication that P tail is 1 minus that. So really there's only one degree of freedom to choose here. And we'll put that degree of freedom here. P of head. And P of head can vary between 0 and 1. And here we're going to draw the entropy of the distribution as a function of P head. First, let's write it down algebraically. It's this equation, right? Any one of these, but I like this one. Except I goes only over two values, I equals 1 and I equal 2. So it would be P head times log of 1 over P head plus P tail, which I'm going to write as 1 minus P head, times log of 1 over 1 minus P head. This is a function of a single parameter. And the parameter is limited to lie between 0 and 1. So we can actually draw here the function that represents entropy is a function of P head, probability of head. Can you help me draw that? What would be the value at 0? What is the entropy of flipping a coin that has a probability of 0 of landing on head? 0. What is the entropy of flipping a coin that has probability of 1 of landing on head? 0. We start on ending 0. What about a fair coin? A fair coin probability of head is 1/2, right? What is the entropy of flipping a coin that is fair? Can somebody say, can everybody say?
1 bit.
1 bit, thank you. So 1 would be here. 1 bit would be here, and that would be here. Now you can write a small program that would actually plot this, and I can tell you that it would look something like this. Oops, that was meant to be here. So this is the shape of the entropy function with a single parameter. You see it's bound between 0 and log k, where k is 2, so log 2 is 1. So here it's bound between 0 and 1. And this tells you the efficiency of different coins. If you use coins to communicate your information, a fair coin is the most efficient, and if you move away a bit too far from fairness, you drop pretty quickly. So you can actually calculate at what point it will be, let's say, half a bit. And using that kind of weighted coin would be half as efficient. You'll need twice as many flips to convey the same information, on average. This is question.
Is the entropy function actually quadratic or is it just like that?
It's not quadratic. It's definitely not quadratic. In fact, you can, ignore the h here. Think about it just as a parameter. Or write it like this. Minus p log p minus 1 minus p log 1 minus p. It doesn't look quadratic. It's not a polynomial. It has a log version in it. But you're right. It's certainly curved like a quadratic. It's kind of U-shaped. Now, this is true not only for k equals 2, it's true in general that the further the distribution is from a uniform, the lower the entropy. Highest entropy is attained when it's uniform. Okay, one other property of entropy that's really, really important, and is not trivial. This, you could say, is kind of easy to derive. Given two distributions Pi and let's say Qi, this is a small p, or equivalently you can call them big P like this and Q like this. Two distributions, they're both probability distributions, so they both consist of numbers between 0 and 1 that sum to 1, but they're a little different. If you write the entropy of P I'd like you to be able to write this without much thinking. Let's assume that i's go from 1 to n in both cases, so they are distributions over the same events, the same set of events. Now I want you to compare this to a slightly different construct. This is not a mistake. It's P here, but it's Q here. This is not entropy. We did not define what this is. This looks like entropy, but it's slightly mutilated. Okay? Let's first try to build an intuition for this, what this might be. How did we get this? We got it because we took the average value of this. We defined this as the information in event I. And we took the expectation of this information under the distribution P. Right? This is how we came up with this formula. The expectation is achieved by summing over all possibilities weighted by the probability of that event. How can we interpret this? Suppose there's a set of events and you know the probability of each event. So you're Mr. P. And then Mr. Q has a different notion of what the probability of these events are. They think that the probability of these events is Q1 through Qn, not P1 through Pn. Remember we mentioned before that information is a subjective notion. Same events, different people have different expectations, they will get different amount of information or will be differently surprised. Right? But there's a difference between the two of you. The difference is you're right and they're wrong. The real events come from the distribution P. This is where the asymmetry comes in. So what this will measure is how surprised will your friend Mr. Q be when they observed events coming from the distribution P. So we now introduce the distinction between the distribution from which the events actually came and the distribution in the head of the observer. Now here's the interesting relationship. It's always guaranteed to be the case that the entropy, the real entropy, is smaller than or equal this expression for any Q. And in fact it would only be equal if P and Q are equivalent, if P equals to Q. So if I just say these are not the same, then it's not equality, it's a strict inequality. Now there's nothing inherently different between P and Q. The difference is who was right about where the events come from. In fact, if both of you keep the same estimates in your head, the same expectations, and now you go and observe events that come from Q, then your friend will be right, and then there will be a different inequality. In fact, the other inequality would be sum of Qi log of 1 over Qi is always less than sum of Qi log of 1 over Pi. This is the average surprise of a person observing events coming from distribution Q when in their head they believe that the distribution is Q, and this is the average surprise of somebody observing the same stream of events coming from the same distribution Q, but in their head they think that the distribution is actually P. So you and your friend disagree about the true probability of events in the world, or the true likelihood of different events, if there is such a thing. You can arrange a little competition. You can stand there and watch the events coming in and record your surprise. You need to do it over a very long period of time. But if you do, in the limit, if one of you is right, then they will have an average surprise that is guaranteed to be lower than of the other one who's not right. I didn't tell you what happens if both of you are not exactly right. But as long as you assume that one of you is right, that person will have lower average surprise than the other person. Questions? Please. How do you prove it? I think you prove it with concavity of log, of the log function. So it's actually true not just for log, but for any concave function. So it can be proven from something called Jensen's inequality. Jensen's inequality says that the expectation of a log, expectation P of a log, is related to the log of the expectation, and the order of that, I always need a minute to remember which way it goes. So this is the expectation of the log, so it goes this way. And it's true not just for log, but for any concave function. And you need just a little bit more trick. This is already in the form of expectation of a log. Actually, this is log of 1 over P, so it's probably the other way around. It's probably like this, because when you convert it into log, you get a negative sign that goes out, and the direction of the inequality reverses. So this is just hand waving, but basically you can prove it from Jensen's inequality. Okay. Any questions so far? I think I mentioned to you last time the game that I played with my kids about guessing the number you chose between 1 and 100. I think I relayed the fact that my daughter used to ask me very inefficient questions. Is it greater than 17? Yes. Is it greater than 18? Yes. Is it greater than 19? Now we can understand better why it's an inefficient strategy. You have 100 numbers, and let's assume that a priori all of them are equally likely. We're trying to narrow it down to which number it is that we chose. The most efficient way to do it is to cut it in the middle. Why? Because if they're each a priori equally likely, then it's equally likely that the answer is less than 50 than it is higher than 50. Forget about the borderline case. I don't care. Let's say 50.5. But basically you want to split the space in such a way that the answer is as likely to be yes as it is to be no. That is the most informative answer that you're going to get. Whereas if she asked me, is it greater than 17, and I say yes, if she now asks me, is it greater than 18, it's extremely likely, it's much more likely than not that I'm going to say yes again. Which is equivalent to her flipping a coin that's heavily biased. That is very likely to come down on yes, not on no, and therefore the average amount of information she's getting is small, and therefore she will on average need more coins, more coin flips or more questions than I would if I used the splitting technique. I say average because she could be lucky. Maybe my answer is 18, in which case she would get there much faster than I would if I used the splitting method. But on average, assuming that a priori the choice of my choice of number is uniform, I will get there faster. How fast will I get there? Log of k, log of 100. Can you get there faster on average? No. You should be able to answer that. You cannot get there faster on average. It is the most efficient strategy on average. So this goes to our notion of collecting training data. If training examples are expensive, either in money or in time or in some other commodity, and you want to be judicious in your choice of examples, you should choose examples. If we're talking about a yes-no classification, as in concept learning, you should choose examples where a priori you think that the answer is as likely to be yes as it is to be no. That way you'll get the most information, you'll get one bit of information. If you chose a question for which the answer is most likely to be yes, then on average you'll get much less than one bit of information. Although you might be lucky and you'll get a lot of information. Okay? Okay. I gave you an example from the amount of information in English. It's actually not as esoteric as it sounds. There's been a lot of work on figuring out the entropy of English and of other languages. In fact, I think one of the first processes that Shannon studied when he invented information theory and came up with the notion of entropy is the entropy of natural language. And since he was here, he studied English. So how do we figure out, if you think of language as a stochastic process that has a distribution over words or over sentences, what is the entropy of that process? What is the number of bits per word or per character? How do you even begin to figure it out? Well, let's try. Let's assume, for simplicity, that we're dealing with English and it has 27 characters. It's A through Z plus a space. Because if you're going to look at a stream of characters, you want to know where the spaces are between the words. And let's assume, for simplicity, that English has 100,000 words. In fact, English has significantly more than that. But how many I can't tell you, because the definition of a word is a fuzzy thing. First of all, the languages keep evolving and changing all the time. And do you count proper nouns as words or not? Well, some words are half proper noun, half not. It's very hard to define exactly what's the word. If you have a possessive, like apostrophe s, does that make it a different word? If it's a plural, does it make it a different word? If it's a conjugation of a verb, do you call it a different word, and so forth? And in some sense it's arbitrary. But 100,000 is a reasonable order of magnitude for a language like English. In some languages it's much, much higher. But it has to do with the definition of word in other languages. So in German, for example, you make new words all the time by putting together noun phrases and taking out the spaces, so to speak, and you have one word, and it is considered a word, even though nobody may have put it together before. But it's a perfectly valid word. Well, is it just because you don't put spaces there? So the notion of a word is not that well defined, but 100,000 will be a fine approximation. Let's first assume a very simple process of generating characters. Assume letters or characters are generated independently okay? So let's forget for a moment about the notion of word and just look at it as a stream of characters. You have 27 of them, and every time you push a button you get another character. What is the entropy of this process? Well, it depends on the distribution of the characters. Let's first assume that it's a uniform distribution. So 1A would be uniform distribution. What is the entropy of this process? You should know the answer to that. No, we're not dealing with words, we're dealing only with characters. There are 27 characters, they're each equally likely. Every time you push a button you get a character. What is the entropy? Log of 27. Log of 27, which is 4.75 bits per character. I use character and letter independently. I'm sorry, interchangeably. So letters and characters are the same thing. So if indeed language was generated by uniformly choosing one letter at a time from a set of 27, the entropy of that would be 4.75 bits per letter, per character. Now, we all know that not all English letters are equally likely. What is the most common English letter? E. If you don't count space. In fact, even if you count space, I think that E is more common than space. Is it? I'm not sure. So I can tell you how common space is. An average length of a word in English is 5.5 characters. So if you think of a word as including the space at the end, that's 6.5 characters, and 1 over 6.5 is the frequency of space. E is somewhat comparable to that. There are roughly as many as E's as there are words in running text. What's the second most common letter? T. And after that, A. And after that, it begins to vary depending on the kind of text. So, and nice little mnemonic to remember that is Eta Owen Shredelu. Eta Owen Shredelu. You may not need it, but people who work in language remember that. So, E-T-A-O-I-N Shredelu. This part varies. Are you dealing with newspaper text or spoken language or formal language or many different genres of language? This part really doesn't vary much. When you get down to this level, there's some changes. How many of you have played Hangman before? Okay, so it's a game where somebody writes down a secret phrase and you guess one letter at a time. And if you guess a letter that's in their phrase, they show you where it is in the phrase. And if you guess a letter that is not in the phrase, you get one step closer to getting hung. My kids play it a lot, and they know Eta Owen Shredelu by heart. They just go straight for the E, and then T, and then A. And then my daughter came up with this incredibly hard phrase. And I got hung. And the reason is I used my Eta Owen-Schroeder-Lew technique to be most efficient on average, and all I got was this. O here and O here. 2 words, there's a space here, 2 words, 4 letters each. And I went down the list of words by, list of letters by order of frequency. And for the life of me, I couldn't figure it out. It turns out, after I showed her the frequency, decreasing frequency of words, she chose a phrase that comes almost entirely from the very end of the frequency list. Can anybody guess what this is? There's no E in it, there's no T, there's no A, there's no I, there's no N, there's no S, no H, no R, no D, no L, and no U, which is incredibly unlikely if you just choose a word at random. I'm sorry, I was wrong, there is an N. But I still, okay, I gave you too much. This still was too hard for me. I didn't know what this was. And I gave you too much and I gave you the wrong information. There are 5 here. I can't spell. I can't spell, but it's still difficult and I still got hung. And the answer is knock knock. Will teach me to learn to spell next time. But she did choose knock knock. She basically went for letters all the way at the very end. C, K, Z are at the very end. Moral of the story is, if you know somebody's expectations, you can take that into account, and it shows you that I'm only most efficient on average when I follow the strategy. Okay, so now that we know the distribution, or if you don't know the distribution, you take a large amount of text, you count the number of letters, each letter, and you use that to estimate the true probability distribution of letters in English. Oops, I have to let you go. If you do that, you have non-uniform but still independent choice of letters. So now the model is you choose a letter every time independently of the previous letters. But when you choose it, you're more likely to choose E than any other one, and you're likely to choose T and so forth. You choose it proportionately to their frequency in the language. And the entropy then, is it higher or lower? Lower. Cannot be higher than the uniform distribution. Okay, remember that? Uniform distribution is always the highest. Any other non-uniform distribution is lower. 4.03 bits per character. It may not seem like a big difference, but it's actually a very big difference. And that's not the end of it. We're going to work and bring it down further by making more and more accurate assumptions about the source from which these letters come. Alright, see you all on Tuesday in 5409.